Now the SVD, right, has various interpretations. Okay. Now I am going to write 4 of them here, 3 of them in fact, and then right, it's up to, okay, and depending upon what you are dealing with, you would interpret it accordingly. One, the SVD is actually a generalization of the idea of, it's a generalization of the idea of diagonalization, of the notion of diagonalization to rectangular matrices, right. Until now we are only talking about diagonalizing, covariance and all that, right, square matrices, basically notion of diagonalization to rectangular matrices. See, even for circulant and all, we had always assumed everything was square, right? And then we talked about diagonalization. Doesn't have to be covariance, even your system matrix, we assumed it to be circulant and then we did. Now we want to extend that notion of diagonalization to non-square matrices, okay, rectangular, or they are called non-square matrices, okay. But the same will also be useful even if you had a square matrix, but the notion is an extension. 2, it can be looked upon as a data dependent transform, looked as a data dependent unitary transform. This is also another way to look at it, is it's some kind of a unitary transform, data dependent unitary transform, okay, which basically means that you should be able to expand a given image in terms of an orthonormal basis, but then the only thing is the basis images themselves would then come from the image itself, just like a PCA. But then in PCA it was a non-simple thing, right? You had many images from which you computed your eigenvectors. Here it has to be something like that image, a basis corresponding for a basis that works only for that image. You change that image, you can't use the same basis, right? This was not the case with respect to PCA. I mean, you could just have this set of eigenvectors, and then if I give you another face, you could use it. You can't do that here. But then the notion of unitariness, everything is fine, okay. Because we are also talking about unitary transform, I thought we should definitely include this point. 3. Another way to look at it is, it yields the best low rank approximation of course a matrix in the Frobenius norm sense. So what this actually means is that if I actually give you the Frobenius norm sense. So what this means is, if I actually give you a matrix which is, let's say, some A, m cross n, okay, and suppose let's say the rank is m, okay, let's say m is smaller than n and then the rank is m. Then suppose I ask you for an A hat, okay, having a rank less than m, let's say m minus 1 or something, right, some other rank which is less than m. But suppose I ask you which is the best approximation, right, that you can get for this A m n, which is some other A hat, right, A hat m n of course, but then which has a rank which is less than this guy's rank, which is the one that would be closest to this in the Frobenius norm sense. That means if you take norm of A minus A hat, right, in that Frobenius error, right, in that sense, then which one will that matrix be? Okay, it basically means that you don't have to run around to find out what would be that matrix. The SVD will directly give you that matrix. Okay, so it can give you the best low rank approximation in the Frobenius sense. Okay, now this one, right, so this one I think there's a separate point, but it need not be a separate point. So here data dependent transform in the sense that the basis images are derived from the image itself, okay, which actually raises some interesting points which we'll talk about. And then okay, right, so really, right, these are the 3 points. I'm not really talking about applications and all. Applications you can, I mean, SVD kind of, right, is all over the place, pseudo inverse, you name it, right, you used it already for this one, homography. It can be used to compute the PCA, so many things, okay, applications wise. But these are really the 3 main things for us, right? This matters the most because this is what this is how we started all of this, right? We had data independent transforms of a different kind and data dependent. PCA we did already, the KLT. Now the second one is SVD, okay? And then the other points are all related to diagonalization and all, which we've already looked within the context of transforms. This third point I just included because that's actually a nice thing to know, okay, in terms of the low rank approximation. Okay, now what it actually says is that, right, now according to SVD, right, if you have okay, SMN, so if you have a rectangular matrix SMN, okay, then it can be expanded, and now what this is again a standard form, okay, they don't write it as A Hermitian sigma B, they write it as A sigma B Hermitian. This is simply following standard text, okay. So which is why if you look at the eigenvectors and all, earlier we used to say there used to be columns of A Hermitian, now they will become columns of A because of the way the singular value decomposition is. This is a standard way in which they write, so I just want to go with what they write in text. Okay, so it will only mean a subtle change in the way we interpret our eigenvectors, okay. All right. Now the point is this, right? And also see, for example, right, another thing is, when we talk about pseudo inverse and all, right, I mean, when you have a rectangular matrix, you can't even talk about its inverse, right? Generally we don't even talk about, but then there is something called a pseudo inverse, which allows you to even talk about inverses of rectangular matrices. And so that inverse is not really the real kind of inverse, right? That's why it's called a pseudo inverse. You must have read it, right? Somewhere pseudo inverse you guys have read, right? So it doesn't. So those properties are not. They are not exactly the same as what you would know. It's not like a real inverse, but then there are some 3 or 4 properties that it satisfies, which look very clean, right? So an SVD is also used to actually get inverses of rectangular matrices, what's called a pseudo inverse, right? And it's also used in when you want to compute the health of a matrix, right? Which can be found in terms of what is called a condition number. So when you want to compute a condition number, it is computed in terms of the singular values of that matrix. Again, right, we can use SVD to compute the health of a matrix and so on. That is something that will come up later, the condition number and all, when we do okay, 2 topics away from now, but at that time, right, we'll talk about it. We'll actually use the SVD at that time, okay. But right now, okay, what this means is that A is M cross M, okay, this is M cross N, and B is N cross N, and A and B are individually unitary. Okay, it doesn't mean that AB Hermitian is identity or something. A Hermitian is identity, BB Hermitian is identity, are individually unitary. Under some special cases, A can be equal to B, are individually unitary. But generally, right, so it means that A Hermitian is equal to A Hermitian A is equal to identity, but this identity will be M cross M, and B Hermitian, whatever, B Hermitian B is equal to BB Hermitian is equal to I, this will be N cross N. Okay, so these 2 I's are not the same. Now this guy, right, is called kind of diagonal, okay, even though, right, it's not really square, but we call this a diagonal matrix because of the way it is structured. See, for example, and the entries, right, of entries of sigma, that is which are kind of non-zero, the non-zero entries of sigma are called the singular values, of S, the singular values of S, okay, which is why it is called a singular value decomposition. And by the way, right, SVD also has an interpretation of a encoder, a decoder kind of interpretation. So many things to it. Okay, so we just look at something that is just useful for this course. Okay. Now, now what this means is that if I try S Hermitian S, okay, all the while, right, I'm still sticking with Hermitian thing. Okay, so if I do or else, okay, let's do SS Hermitian. Maybe let's do that first. SS Hermitian will mean that we have A sigma B. So if you're really wondering, right, what these A and B are, okay. Now another way to look at what is A and B mean is if you try SS Hermitian, there will be A sigma B Hermitian, and then S Hermitian is B sigma Hermitian A Hermitian. Right, and because we said B Hermitian B is identity, this turns out to be A sigma Hermitian A Hermitian, right? And since right, this matrix is of the form SS Hermitian, it is automatically symmetric, right? It's actually Hermitian symmetric, and therefore, right, you can kind of look upon this as an eigenvalue eigenvector kind of a decomposition of you say SS Hermitian, eigenvalue eigenvector decomposition, which we saw, right, only say recently. So which then means that now the only change is that the eigenvectors, right, are all the columns of A now, because of the way this SVD you write it. Okay. So the eigenvectors of SS Hermitian are but the columns of A, and then the eigenvalues of SS Hermitian are sitting here. Okay, in this matrix sigma Hermitian, which will now be diagonal. Okay, which will be square and diagonal. Then you can also look at what happens to S Hermitian S, right? And then okay, right, depending upon the rank, right, this structure will change, right? Whether you get all zeros as the last row or whether you don't get them depends upon which is depends upon the rank of S. S Hermitian S, if you do, that gives you B sigma Hermitian wait a minute, B S Hermitian, okay, A Hermitian, then A sigma B Hermitian. So that gives you B sigma Hermitian. This is identity sigma B Hermitian, and therefore, right, the eigenvectors of S Hermitian S will now be the columns of B. Okay. Now, what this actually means is that so this A and B, right, really if you think about them, A and B are really eigenvectors. They contain eigenvectors of, in one case, SS Hermitian corresponding to A, and then B contains the eigenvectors of S Hermitian S, right. So therefore, this A and B are not something that are kind of say dropping from somewhere, right. So which is also the reason why this kind of a dependent transform, right, when we say the basis images and all, they are all coming from in fact A and B, right, because the basis images get formed from the columns of A and B, and because A and B come from S itself, in one case SS Hermitian, another case S Hermitian S, therefore we say that the basis images depend on the image itself. Okay, so if you change the image, for example, if I go from S to some other image, even if it has the same dimension, it doesn't mean that A and B will have to be the same, right. A and B will then automatically change if I change my S, which will then mean that the basis images will change. So if I just want to, let me just take a small example, right, just to illustrate how it might look like. So if you take S, let's say for example 2 cross 3, right, what it will mean is that so your sigma, right, will then be 2 cross 3. What this means is it will look like sigma 1 0 0 0 sigma 2 0. Okay, so these are called the singular values. Okay, which then means that and of course A and B will accordingly have 2 cross 2 and 3 cross 3 as that is a dimension. And if you look at sigma Hermitian, right, that will look like sigma 1 0. Okay, and one more thing, right, these singular values, they are actually defined as the positive square root of the eigenvalues of SS Hermitian or equivalently S Hermitian S. So if you look at it, right, so sigma 1 0 0 0 sigma 2 0, and then sigma Hermitian will mean you will have sigma 1 0 0 sigma 2 0 0. So you got like 2 cross 3, and then you've got like 3 cross 2, and this will give you sigma 1 square 0 0 sigma 2 square, right. So as you can see, right, clearly these are the eigenvalues of S, right. What is that? So which was this guy, SS Hermitian, right. So these are the eigenvalues of SS Hermitian. So this is Hermitian, and the positive square root, right, of these eigenvalues is sitting here as a singular value, which is sigma 1 and sigma 2. If you do the other way around, sigma Hermitian sigma, then you will get time, right. So sigma, so that is like sigma 1 0 0 sigma 2 0 0, and then sigma 1 0 0 0 sigma 2 0. So this is 3 cross 2, this is 2 cross 3, that will get 3 cross 3 will get sigma 1 square 0 0, then 0 sigma 2 square 0, and then the last row will all be zeros. Okay. Now, right, I am going to leave it as an exercise, right, for you to show that the SMN, right, that we wrote, okay, that I wrote as A sigma B Hermitian, okay, I will leave it to you as an exercise. Please show that this can be equivalently written as, suppose let's say, right, suppose S has a rank R, which means it has R is a non-zero singular values, then it can be written as R, what should I use here, I, okay, let's use, okay, P, whatever, it doesn't matter, equal to 1 to P, where where let's say P is the rank of S. Okay, if S is full rank, it will be smaller of M or N, otherwise it can be less than that number. So I equal to 1 to P sigma I AI BI this one Hermitian. Okay, so AI is actually a vector now. Okay, this I am going to leave it to you. Okay, AI is the ith column, of A, and BI, okay, BI is the ith, so BI, okay, I am not going to write BI Hermitian, BI is the ith column of B. Okay, which is why I said that there is a small sort of a difference between the way we did prior, when we did KLT, it was like column of A Hermitian or psi Hermitian, but because of the way SVD is, the standard form of SVD is A sigma B Hermitian, and therefore it will turn out that this will come out as columns of A and columns of B. Now, if you look at this AI BI Hermitian, right, this is like a column vector multiplying a row, right? AI is coming from A, BI is coming from B, and together, right, when you kind of multiply this, okay, so this kind of sort of an outer product, right, that you have here, this is the basis image. So these are the basis images, and again, right, I am going to leave it to you as an exercise to show that if I take inner product of SMN with, let's say, AJ, okay, BJ Hermitian, this will give me sigma j. Okay, this follows the same thing. Okay, I mean, so now what I can look upon as your, so if you look upon it as an image expansion problem, and if you look at S as an image, now in this case it's a square image, not square, it's actually a rectangular image, like M cross N. That image can now be expanded in terms of the basis images that you obtain by doing AI BI Hermitian. And these AI BI Hermitian, so what kind of a weight should you attach to AI, because, right, we need a weighted linear combination, right? What kind of a weight should then be there? That weight is actually the singular value itself. The singular value itself that you can again obtain by either doing SMN, you can show that inner product of SMN with AJ BJ Hermitian will give you this. Okay, now here is where, right, it's interesting, because the basis image is coming from A and B, okay, that is vectors of A and B. And also, right, it also means that, one more interesting thing is, suppose, let's say, right, S is an image. Suppose I say that S is some, let's say, 64 by 128. Then if I wanted to transmit S as it is, right, let's look at the image expansion problem. Suppose I transmit the image itself, then how many bytes will I need? It's an intensity, right? So let's assume we've got like 256 gray levels. So 1 byte for each gray level. So 64 into 128, okay, right, that many bytes. Now if you are transmitting in this manner, what can you say about, so 1 byte for an integer, no, that is if you are transmitting a gray level. How many bytes will you need? See, you won't send, you will not want to send AI into BI Hermitian the whole matrix, right? That doesn't make sense, because then, I mean, you would end up, I mean, why would I want to even use this to send? Because even in one image I would have consumed my whatever, the whole size. I would rather send this vector and that vector, and then this outer product somebody can do at the other end, right, to get that whatever n cross n matrix, right. How many entries are there in AI? AI will have 64 cross 1, correct, that many entries in it. BI will have 128 cross 1, right, or Hermitian is 1 cross 128. Now how many bytes do you think you will need to send AI and BI? A is actually a unitary, right, I mean A Hermitian, A matrix is unitary. Therefore, these numbers, right, need not have to be integers, right. They can, it can even be a complex number for all we know. So normally, right, you would assign about, what do you do for float, 4 bytes or something, right? If you take it as a float, so it will be like 4 bytes minimum. 4 bytes times 64, okay, and then 4 bytes times 128 for BI. If you want to send one sort of a basis image, and then this is a singular value, which is again a float. That's like plus another 4 bytes, right? Now you have to see how many such basis images can you add. Again, right, you will go by the significance of the singular value. Something which is less significant, you may not want to transmit, right? So you may want to pick the most significant singular values, only add them up. So you should be able to show that, right, that beyond a point, let's say I equal to 1 to R, right, there may come an R which is less than P, by which time I would have exceeded the size of S itself, right? It can happen, correct? So in that sense, right, nobody uses SVD to do this kind of a compression and all, okay? But I'm just saying that theoretically the possibility exists. I mean, you can ask how many terms should get involved in this expansion before I exceed the size of S if I had to transmit S that way. Right? You could ask that question, but normally people don't really use it for that. But then because we are doing this image expansion business, right, I thought, it's important for us to know at least that such an expansion is possible. Whether you do it or not is another thing. Right. Now, what you might want to ask is the following, right? Suppose I do say S hat, okay, M cross N, such that, right, I use only, let's say I is equal to 1 to R terms in this. What is that? Sigma I, AI, BIC Hermitian. Okay, R less than P. See, if I use all of P, then of course I reconstruct S exactly. Correct? But suppose I don't use, now let's assume that it's all ordered. Okay, my singular values are all ordered, and I just take the top R terms, right? So R singular values, and those are the ones that I use. Now you might want to ask, what kind of an error, right, will I now make in terms of approximating S by SMN, right, by this S hat, right? So suppose I call that as the error matrix as E. Let me call this E M cross N is S minus S hat. Right? Both are of course M cross N, right? Now this will be summation I is equal to R plus 1 to P sigma I AI BI Hermitian, correct? So all the terms that we have left out, that will be the matrix, the error matrix. Now, if I want to, let me write this as E, okay, let me not write this Mn, okay, we know that these dimensions, and because what I want to represent is, suppose I write E M comma N, I mean the mnth entry of E, Suppose I examine the mnth entry in this matrix, then that can be shown to be, I just leave it to you, or you already know what it is, R plus 1 to P sigma I AI M BI N star, okay, down to the scalar expression now. BIN star, where the star is of course a complex conjugate. Now E star Mn, right, will be what? Summation I is equal to R plus 1 to P. Now sigma is anyway real, therefore that just stays like that. Now you will get the whole star, right? So this is simply the whole star, that will be A star IM BIN. Okay, now if you look at magnitude, right, EMN square, that means at the mnth entry in E, what is the square error, the magnitude square error, that we know is EMN into E star Mn, or in this case that will be summation I is equal to R plus 1 to P sigma I AIM BIN star into, let's say, summation, let's use some J is equal to R plus 1 to P sigma J AJM BJN, star, okay, star BJN, okay, because E star Mn, no. So then this will be what? So if you just collect all terms where I equal to J, so this will be like R plus 1 to P sigma square I AIM then A I equal to J, right. So, A I M complex conjugate into B I N star and B I N plus a double sum over I is equal to P, what is that, R plus 1 to P, J is equal to R plus 1 to P, but I not equal to J, sigma I, sigma J, A I M, A J M star, B I N star, B J N, right. If you just expand this, then now for example, now if you see this quantity, right, this is but magnitude A I M square, this is magnitude B I N squared. Now now if you want to compute the Frobenius norm of this matrix, right, that will be the sum total error, right. When I do S and approximate S by S hat, what is the sum total error that I am making across all the entries in that matrix? That will be like that. For that, right, what should I do? I should sum it up over all m comma n, right, over all the entries of this error matrix. So, suppose if I do that, then summation m n, right, over the size of the image, magnitude E m n square, right. This will be the right, this will be the Frobenius norm square of E, the error matrix. So, this now will be equal to summation m n, right, and then whatever you had there, I mean, right, you had summation, what was that, I is equal to R plus 1 to P, then you had sigma I square, then what was it, some magnitude A I M square, then magnitude B I N square plus summation double sum I not equal to J, you had sigma I, sigma J, then whatever A I M, then A J M star, what was that? A J M star, then B I N, whatever, B I N, and then B J N star, right? B I N and B J, oh no, B I N star and B J N, okay, B I N star and B J N. Okay, this is what you had. So now if you actually push this summation inside, right, and then if you just pull out, so I is equal to R plus 1 to P, sigma I square, push this m inside, you have magnitude A I M square into summation, push this n in square, B I N square, plus then summation, let's keep this I, okay, yeah, let's keep this I outside, and then sigma I, and then J, sigma J, and then summation m, A I M, A J M star into summation n, B J N into B I N star. Okay. Now this we know is simply the norm of the right ith, this one, the column of A, and because A Hermitian is identity, therefore this is 1, correct. Okay, because A and B again form an right orthonormal set of vectors, orthonormal basis, right, orthonormal set. This is also 1. Now if you look at it, right, here I is not equal to J, right, and therefore this is like saying that this summation will give you 0, correct, because I is not equal to J, no. So it's like taking the right inner product of AI, the AIth column with, let's say, AJth column, which we know, right, they are orthonormal. And similarly, here also I is not equal to J, therefore, right, this is also 0. Therefore, right, this simply boils down to summation I is equal to R plus 1 to P sigma I square, right. So which we know is basically the eigenvalue of right, sigma I square is what, I mean, all the eigenvalues of SS Hermitian or S Hermitian S. So in the PC also we had written something similar, right. We had said summation lambda I of all the eigenvalues that we had left out. See that, right, you get a very similar expression for the SVD, except that now this is exact. Okay, this, for example, if you take a matrix and approximate it by some right, by whatever, right, if you just collect the first what are we saying, R terms, right, and then if you do this expansion and if you compute the error, this is exactly what it will be. In terms of a PC, it's more like a mean square property. This is like for that image, this is what exactly will happen, okay, if you make the approximation. Now incidentally, right, there is also a theorem which we will not prove. What it says is that among all matrices right? That among all the matrices that have, suppose you approximate S, right? In this case, S m cross n with an S hat m cross n, where the rank of this guy is, let's say, rank of S hat is equal to R. Suppose, right? Suppose say that I want the rank of S hat to be R, and then it should be as close as possible to S in terms of the Frobenius sense. That means norm S minus S hat, square, right, should be as small as possible in the Frobenius sense. Then this is the guy. Okay, so if you wanted to compute that matrix, you would just do exactly this SVD. You will take the first R terms, of course, order the singular values, take the first R terms, whatever is that matrix that you get, right? It will have of course, this norm error will be this exactly the summation sigma I square, and wherever you go in the world to pick a matrix of this dimension m cross n and of this rank R, this is the matrix that will give you the smallest, will give you the best low rank up. It's called low rank because you're going like one rank, you're going lower rank than S, right, and trying to get an approximation to S. So the best, which is what was my third point that I had written. So this is the best low rank approximation for S. Okay, so SVD can be actually used for that. This I derived just to show that, right, what will be the what error, right, will you be making. Okay.